Hello, ladies and gentlemen. Welcome to Edu-ca-te. Let us talk about classifying stationary points as local extremes or saddle points. Remember that local extremes, basically we are talking about a local minimum turning point. So this is a local minimum as well as a local maximum. These are known as local extremes all together. But the saddle points, they are not minimum, they are not maximum, but they do have a gradient of 0. So we can classify them as a stationary point. So now remember that the local minimum, it looks like this, it is the lowest value. And then the local maximum, it looks like this, it is the biggest value. So basically those are the local extremes. And then this is how a saddle point looks like, because if you put this tangent, a tangential plane on it, it's going to have a gradient of 0. So it means it's a stationary point indeed, but it is not the maximum, it is not the minimum, it is actually in between. So we classify it as a saddle point. So now remember that in our previous video we have explained how do you get stationary points. You just equate the gradient of that particular function or the partial derivative, you equate it to 0, because you know that the gradient of a function at its stationary point is 0. So now let us look at how do you classify now to say that the stationary point that we have, is it a local minimum, is it a local maximum, or is it a saddle point? So you do what we call is the second partial test. So the second partial test needs two things. It needs you to get a discriminant, the value of d, and it also needs you to use the value of a. So basically the discriminant, you get it by multiplying the value of a and c minus the value of b squared. But basically you're asking yourself, where do I get all these a, b, c values? So to get a, you need to do the second partial derivative in terms of x. To get b, you need to do the second partial derivative of the partial derivative of y in terms of x. We're going to see how that works. And then the third one, which is c, you need to do the second partial derivative in terms of y. So basically, after getting those values a, b, c, that's the first step. You follow the steps as I'm telling you here. You get a, you get b, you get c. And then after that, you interpret your results. So to interpret the results, you say that if your discriminant, after substituting a, c, and b here into the equation, if the discriminant is greater than 0 and the value of a is also greater than 0, then you have got a local minimum turning point. And then if your discriminant is greater than 0 but your a is less than 0, then you have a local maximum turning point. And if your discriminant is less than 0, it doesn't matter the a value, then it's known as a saddle point. So basically, that is the reason for doing the second partials test, because you want to find out what type of stationary point do we have. Because remember that stationary points all have got a gradient of 0, or the gradient does not exist. So in a sense, we need to be able to do the second partials test and try to find or classify our stationary points. So now let's start here with this statement. It says find all the stationary points and classify them as local extremes or as saddle points. So now the function is f of xy is equals to x cubed minus 6xy plus y cubed. So basically here we do not even know the stationary points. So we need to first find the stationary points, the ones that have got a gradient of 0 or that have got no gradient at all. So here to find that, you need to first find the gradient of f xy. And to find the gradient, remember, you just take the partial derivative of the function with respect to x I plus the partial derivative of the function with respect to y j. In this case, we only have got x and y. So here, if you take the partial derivative in terms of x, you're going to remain with 3x squared minus 6y. And then this is all under I. Do watch my video on partial derivatives. You understand what I'm doing here basically. This one is x cubed. When you find the partial derivative, is 3x squared. This one is negative 6xy. It does have x in it. So if you find the partial derivative, you get negative 6y. and then this is I. And then now you add this to the partial derivative in terms of y. This term has got y in it, so if we differentiate it in terms of y, you will remain with a negative 6 times x, negative 6 times ax, because remember derivative of y is just 1, so this is negative 6x, and then this is plus, if you differentiate this in terms of y, you are going to get 3y squared, and then this is j. So basically this is the gradient of the function given by xy, this multivariable function. So now that you have the gradient, you now need to equate the gradient to 0 so that you can find the stationary points first, because you cannot classify points before you find them. So now let us find the stationary points. We are just going to equate each partial derivative to 0. In this case, you're going to equate 3x squared minus 6y. You equate this to 0. And you also equate negative 6x plus 3y squared. You equate this to 0. So now we're just going to solve this simultaneously. So to solve this simultaneously, I think the best thing that you can do here, it is to deal with this equation because it is simplified. So you can just say 6y is equals to 3x squared by transposing negative 6y to the other side, and then you divide by 6 on both sides if needs be. So here you can just divide by 6 on both sides. So we can just divide by 6 on both sides, but we can just manipulate this by dividing by 2. You can just manipulate this by dividing by 2, and then this will be 3y is equals to 3 over 2x squared, and then now you are just going to square both sides. Okay, but then it's fine, the mathematics is not mathematicking there, but then you apply whatever technique that you think of to, to solve here. So let's just try to make y the subject of the formula rather, so that this thing becomes easier. So here, if we make y the subject of the formula, 6y is equals to 3x squared, and then in this case, y will be equals to 3 over 6, which is 1 over 2x squared. So this is the y as the subject of the formula. You now just substitute this into this equation and solve simultaneously. So now this will be negative 6x plus 3 times 1 over 2x squared is equals to 0. Remember that 1 over 2x squared, it is the whole value of y, so you substitute it with this y here. And simplifying this is negative 6x plus 3 into 1 over 4x to the power of 4 is equals to 0. And then this will be negative 6x, and then this is basically going to give you 3 over 4 plus 3 over 4x to the power of 4. This will give you 0. And then now you have to solve your x using whatever mathematics that you can use here. Okay, so basically if you use maths here, you can just take out x and you remain inside with negative 6. You remain inside with negative 6, and then this is plus 3 over 4x cubed. So negative 6 plus 3 over 4x cubed will be equals to 0. And then now you can see that here, using maths, you can say that x is equals to 0, and then this whole thing is also equals to 0. So in this case, you can have two options. X is equals to 0, and you can also have negative 6 plus 3 over 4x cubed is also equals to 0. And then here, if you transpose 6 to the other side, this will be 3 over 4x cubed is equals to positive 6. Now you solve for x. So you divide both sides by 3 over 4. So let me just take this here. You divide both sides by 3 over 4. You remain with x cubed will be equals to 6 divided by 3 over 4 will be just 24 over 3, which is 8. So this will be just 8, if I see correctly here. And if you take the cube root of 8 on both sides there, you're going to get that x can also be positive 2. What a long thing to do. So basically that's the maths here. You are doing what? You are trying to find the stationary points. Look at this. We have got two x values. We have got x is equals to 0 and we also have got x is equals to 2. So we have got two options here. So do not be misled and think that the x is equals to 0 is of no significance. It is a stationary point as well because you obtained it by equating the partial derivatives to 0. So basically here, since we have obtained it by equating partial derivatives to 0, we consider it as a stationary point as well. So here, let's find our y value. So we can find our y value here by substituting 1 over 2 into 0 squared. So when x is 0, y is also 0. So you've got one stationary point given by the x value 0 and the y value 0. And you also have got another x value here, x is equals to 2. So you take 2, you put it into the equation, y will be equals to 1 over 2 times 2 squared. In this case, this is 1 over 2 times 4, and this is just half of 4, which will give you 2. So here in this case, another point, another stationary point q, will say that when x is 2, y is also 2. Here we go. So you've got two stationary points in this particular case. You first find all the stationary points that are in the equation by equating the partial derivatives or the gradient to 0, because we know that at the stationary points the gradient is 0 or it does not exist. So in this case, now we want to classify these 2 points as saddle points, or we want to classify them as local extremes. It's either local minimum or local maximum. So now we're going to now apply our second partials test. I have just put this to remind you here how to find it. So now basically our function was f of x y is equals to this was x cubed minus 6xy. So this is x cubed minus 6xy, and then this is plus y cubed. So this is plus y cubed. So this whole calculation that we have done so far, it was to determine the stationary points. Now we want to do what? To classify the stationary point as either local minimum, local maximum, or a saddle point. So now basically we have to find the value of a. Remember, we said that to find the value of a, you have to take the second partial derivative. So we have to take the second partial derivative in terms of x. In terms of x. So basically it means that you are going to differentiate the partial derivative of this function in terms of x. So basically remember that the first partial derivative here of f in terms of x, we have calculated it before and we found out that it is 3x squared minus 6y. We can also do it here and just differentiate the function in terms of x, basically. So this is 3x squared minus 6y. So this is the first partial derivative with respect to x. So we can further differentiate this again with respect to x. That's where we get the squared to say that we are now doing it for the second time. So basically here, to get our value of a, we need just to take this equation, which is the first partial derivative in terms of x, we differentiate it again in terms of x. So now this will give us 6x. So this will give us 6x. All right. And then now we are done with the value of a. We are done with the value of a. To find the value of b, remember we've said that we find the second partial derivative of f of the partial derivative in terms of y, but now in terms of x. Hey, what a confusing thing. So basically here, I remember that our partial derivative of f in terms of y was given by what? Was given by negative 6x, right? It was negative 6x plus 3y squared. So this is the partial derivative with respect to y. So basically, you found the partial derivative with respect to y by just differentiating these two terms individually. You got negative 6x plus 3y squared, which is what we got here. So now, when you're finding the value of b, to find the value of b, you say that b is equals to the partial derivative, the second one of f, but now you are going to find the one of y, but in terms of x. Hey, that's so complex. It looks complicated, but it's very simple. So basically here, you are going to take the partial derivative in terms of y. This one that we have here, the partial derivative in terms of y, and then you are going to differentiate it again, but you are going to differentiate it with respect to x. So you're going to take the partial derivative in terms of y, or with respect to y. You are going to differentiate it again, but with respect to x, so that you can find the value of b for your discriminant. So basically here you're going to get that b will be equals to, you differentiate this, but in terms of what? In terms of x. So differentiating this in terms of x, you get that b is equals to negative 6. Then now you are done with finding the value of b. Now you find the value of c. So the value of c, remember that it is the second partial derivative of f in terms of y. So it means you are just going to take this first partial derivative, you're going to differentiate it in terms of y. It's more like you're finding a second derivative in terms of y. Okay, so here c will be, if we differentiate this in terms of y, we are going to get 6y. We're going to get 6y. So this is your value of c. That's the first step. You find a, b, c. A, it is the second derivative in terms of x, or you can say that it is the second partial derivative with respect to x. But b, it is the what? It is the second partial derivative of this function. You are going to differentiate the partial derivative in terms of y, but you're going to differentiate it in terms of x. That is why here you start with the partial derivative of y to say that originally you have found the partial derivative of y, and now we are going to differentiate that partial derivative. Now we are going to do it in terms of x. So you've got a, b, c. Those are your values that's going to help you to classify these points as either local minima, local maxima, or saddle points. So now looking at this, let us now do the classification. You find the discriminant. Remember that the first step here is to find the discriminant using that formula. Discriminant is equals to ac minus b squared. So you have the value of a, c, and b. So now the discriminant will be equals to ac minus b squared. And now taking the value of a, it is 6x. The value of c, it is 6y. So you are multiplying them together. So this is 6x, this is 6y, and then this is minus. The value of b here, it is negative 6. So this is minus negative 6 squared. So now the discriminant there will be given by 36xy, 36xy, and then this is minus 36, minus 36. So this is the discriminant at a particular x value. So now, let us now go into the classification. Now we want to see, remember the stationary points that we got here, we found out that we have got two of them. We have got two stationary points. We have got P given by 0 is to 0, and we also have got Q given by 2 and 2. So we have got two of them. We have got P, okay, let me just write here, we have got P given by 0 is to 0, and then you have got Q given by 2 is to 2. So these are our stationary points that we've obtained using the gradients by equating these to 0, the one that we did first. So now remember that for you to be able to determine the type of stationary point, you have to find the value of A. So you have to find the value of A, you have to find the value of D, which is the discriminant. Then now you can tell me the result, or you can interpret. So you have to find the value of A, the value of D, and then now you interpret. So the value of A here, remember that A is given by 6x. So it means the value of A depends on a certain x value. So in this case, if we are picking the point P given by 0 is to 0, then we're going to substitute 0 into here. So this will be just 6 times 0, and then the A value there is 0. So it's just 6 multiplied by 0. What about the discriminant? The discriminant, you do the same thing. You can see that your discriminant is in terms of x. There is x there in it. So you're just going to put 0 where there's x. So this will give you 36 times 0 times y. Y is also 0 in this case. And then minus 36. So the answer that you're going to get will be just negative 36. And then what would that result be? Remember, we have said in our first slide that if the discriminant is negative, then we classify the stationary point as a saddle point. It doesn't matter the A value. So basically here we found out that we have got a discriminant which is negative 36 at a point P00. So the result here will be a saddle point. So we'll say this is a saddle point just due to this discriminant. Now let's classify Q as a saddle point or a local minima or a local maxima. So here we have got x is equals to 2. To find the value of A, remember that A is a function of x. A depends on the x value. So basically A there would be equals to 6 multiplied by the x value of Q is 2. Then that's going to give you positive 12. And then now the discriminant also depends on what? Also depends on the x and y value. So the discriminant when we're at point Q will be just 36 multiplied by x is 2 and y is also 2. And then this is minus 36. So basically this is going to be 36 multiplied by 4. So we can just say 36 times 2 there, you get you can just say 36 times 2 and you're going to get 72, and 72 multiplied by 2, yeah, the maths is running away. It's 144. So this will be 144 minus 36. So this will be 144 minus 36. Whatever outcome that you get there, you know that is going to be a positive number. Okay. So now let us classify this as a saddle point or a local minima or a local maxima. Here you have got the D value is going to be a positive number. Obviously, if you say 144 minus 36, you are going to get something around 90 something. Yeah, okay, maybe you're going to get something around 108 or something like that. So around that. So it means that this is actually a positive number. So in this case, D is greater than 0. It's a positive number. And A is also greater than 0. So the point Q given by 2 is to 2. It is actually going to be a local minimum. Because remember that we have said, according to how we interpret the results here, if D is greater than 0, meaning that D is positive, and A is also positive at that particular point, then this results in a local minimum turning point. So we can classify the point Q given by 2 is to 2 as a local minimum. So stay tuned for the next video. We're going to do further practice on the on classifying the stationary points as saddle points or local minima or local maxima. Thank you for watching.